lesson in our unit studying quadratic equations. So in this lesson, we're going to learn how to graph quadratic equations, how to solve quadratic equations, and how to use them in real life situations. So today is our very first time looking at what the basic quadratic function looks like and how to graph it using a vertex equation. So just to give you a real life visual of what a quadratic equation looks like, if you look at this bridge going across this lake, you see these arc bases at the bottom of it. Those arc bases are graphed from a quadratic function. So to build this bridge, our engineers needed to understand how to graph a quadratic function and get it usable to support an entire bridge. So let's go over the basics. In a quadratic function, you have at most 3 terms. You have the term that is considered the quadratic term. The quadratic term comes from the term that has a degree of 2. Then you may or may not have a linear term. The linear term is the term that has a degree of 1. And then last, you may or may not have a constant. So the constant's the number that doesn't change because it doesn't have any variables. So that's the backbones of what our quadratic function looks like. When we graph a quadratic function, we get a form called a parabola. So parabola is the shape of all those arcs on the bottom of that bridge. This is the backbones of our quadratic function. So understanding that when I look at a quadratic function in standard form, I'm going to need to utilize these 3 coefficients. A being the coefficient to our quadratic term, B being the coefficient to our linear term, and C being the constant. We're going to use that to find the center point or our vertex in our parabola when we're able to graph. All right, so what I'm looking at is just the basic graph of a quadratic function. So you'll remember when we talked about absolute values having a parent function. This is our parent function because there's nothing being added or subtracted. So we're going to start this off very basic with very little knowledge. And what I'm going to do is I'm going to set up a table of values. So I'm going to do my input as x, and my output is going to be x squared. So I'm going to pick some generic points. And I like to pick about 5 points so that I get a good shape to my graph. All right, so when I plug -2 in, I get -2 squared, which is +4. -1 squared is +1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So now I'm just going to go ahead and graph these 5 ordered pairs. So -2 gives me 4. -1, 1, 0, 0, 1, 1, and 2, 4. Now notice that my graph is not straight. It's not linear. So I shouldn't have a point down here. It's going to curve slightly to give us that parabola shape. Now you'll notice from the bridge picture, this appears to be an upside down arc, but this is actually what the original function looks like. In that bridge picture, those arcs were turned upside down to create the base to that bridge. So this is what our parent function to a parabola or a quadratic function looks like. So now we need to identify some important pieces to this parabola. So in this parabola, you're going to have what's called the vertex. So the vertex is the point that the line of symmetry cuts down through. So you remember from chapter 2, we talked about lines of symmetry. In this case, we call it an axis of symmetry because that's the axis to which we can reflect the left side to the right side of the graph. All right, so our vertex is actually found by an equation, or where that vertex is located, by using those coefficients. So that axis of symmetry is found by taking x is equal to negative b over 2a. Now, what's nice about this, if we can locate where that axis of symmetry is found first, then that's going to help us set up our table of values so that we aren't randomly looking for points all over the graph. Okay, so once we find and establish our axis of symmetry, we're going to be able to build our table of values from there, because we're going to symmetrically go to the left of that point and to the right of that point. Another important place on a parabola is where we cross the y-axis, or our y-intercept. So just like in an equation of a line, y equals mx plus b, that b is our y-intercept. In this case, because it was our constant, in this case our y-intercept is going to be our c. C will be our y-intercept. All right, so if I go back to our basic parabola, oops, I lost it here. If I go back to our parent function of a parabola, you'll see that the axis of symmetry actually falls on the vertical line x equals 0. My y-intercept is also at 0. And my vertex is at 0, 0. So that's before I start remembering to add or subtract any values to my quadratic function. All right, so we see the axis of symmetry, we see the y-intercept. Now let's try to graph another function. All right, so this is the function y equals x squared minus 4x plus 4. Because I have things added and subtracted, it's going to move my parabola around. So the first thing I'm going to do is determine where my axis of symmetry is located. So I'm going to use that formula every time. X equals negative b over 2a. Now remember that we're in standard form. Our quadratic function is ax squared plus bx plus c. So in this equation, my a is the coefficient to my quadratic term, which is 1. B is the coefficient to my linear term, which is negative 4. And C is at positive 4. All right, now I'm going to plug those values in to locate my axis of symmetry. So x equals a negative 4 over 2 times 1. So my axis of symmetry is positive 4 over 2, or 2. So I can go ahead and kind of draw my imaginary line here, and that's where my axis of symmetry is located. That's also where the x value of the vertex is located. So to find the vertex, I'm going to plug 2 into the function. So I'm going to make this y equals 2 squared minus 4 times 2 plus 4. And when I do that, I get 4 minus 8 plus 4 gives me a negative, or 4 minus 8 is negative 4 plus 4 gives me 0. So my vertex is going to be located at 2, 0. There's my vertex. All right, that's also going to be my starting point when I go ahead to graph. So when I go to graph, I'm going to set up my table of values, x and x squared, but I'm going to start in the middle here. And I'm going to start with picking 2 from this 2 here where my axis of symmetry was located. I'm going to pick 2 points to the left, and I'm going to pick 2 points to the right. And I'm going to plug those values into this function here. So I'm going to find f of 0, f of 1. We already found f of 2, and find f of 3 and f of 4. So if I do that quickly, f of 0 is going to give me 4. F of 1 is going to give me 1 when I plug that in. F of 3 is going to give me 1, and F of 4 is going to give me 4. Now remember, if we indeed found that axis of symmetry, then these two values should be symmetrical. Now I wouldn't take that at face value, because if you messed up finding the axis of symmetry, you're going to have different points there. So you want to make sure you plug all 4 of those points in. So now I'm going to plot those on my graph. So I have 0, 4, 1, 1, 2, 0, I already plotted, 3, 1, and 4, 4. And you can see that nice parabola shape being built. And there you have it. So you can see the vertex, my y-intercept is at that +4. And my axis of symmetry is drawn through. Now if I ask you to build the domain and the range, the domain and range, remember, goes left and right. So notice that my graph, if I draw my vertical line, will have a value everywhere to the left and everywhere to the right. So my domain is going to be all reals, and my range is going to be all y values such that y is greater than or equal to 0. Now, with a parabola, because you can have various different parabolas, they can move around, they can go down. You're either going to have a minimum vertex value or a maximum. That means that it is the smallest point in the data set or the largest. Since our vertex is the lowest point on the graph, we're going to say that our vertex is a minimum, and that the minimum value here is at 2, 0. That's the smallest point on the graph. They all continue to get bigger from there. So that's all of our information for our parabola. We're going to try a few more. So here's our second example. Y equals x squared plus 6x plus 5. So again, the first thing I'm going to do is find that axis of symmetry. So I'm using that formula, negative b over 2a. Now in this function, a is going to be 1, b is equal to 6, and c is equal to 5. My axis of symmetry is going to be located at negative b over 2a. So my axis of symmetry is going to be at the value negative 3. So I'm going to go ahead and draw that in there because I know that I want my parabola to be symmetrical to that value. All right, now I'm going to find my y-intercept. So my y-intercept is just c, which is 5. So I know that 1, 2, 3, 4, 5, I should be hitting the y-axis at 5. All right, so now I'm going to build my table of values. I'm going to have x as my input. My output is x squared plus 6x plus 5. Now I'm building it starting with negative 3 in the middle. I'm going to pick 2 values to the left of negative 3 and 2 values to the right of negative 3. If I've done everything correctly, the parabola should build symmetrical to that value. So if you need to take a minute to pause the video and plug those values in, go ahead and do so. When I plug in negative 5, my output is 0. Negative 4 gives me a negative 3. Negative 3 gives me a negative 4. Now this is going to be my vertex, remember, because that's where my axis of symmetry is located. When I plug in negative 2, I have negative 3. When I plug in negative 1, I have 0. Now you'll notice here that I'm symmetrical right around the vertex, and that's what I want to happen. Okay, so I'm a little bit off my graph here, but negative 5 takes me negative 3, negative 4, negative 5, all the way to 0. Negative 4 takes me to negative 3. Negative 3 takes me to negative 4. -2 takes me to -3, and -1 takes me to 0, and I can catch that y-intercept. So you can see that my graph is symmetrical to the axis of symmetry, and there is my parabola. So noting a few important ideas, I'm going to list my domain. My domain for parabolas, left to right, is going to cover all real numbers. My range, however, is going to have the lowest point at -4. So it's going to be all y values such that y is greater than or equal to -4. That means that this vertex is the smallest in the set. So my vertex is going to be a minimum value. We're going to use those minimum values, and it is at -3, -4. We're going to need that important minimum value or maximum value later on. So there you have our parabola, the graph of our quadratic function x squared plus 6x plus 5. All right, let's look at our third example here. So you can see the change is that our a has a negative value to it. So when I'm listing my coefficients, my a is negative. So let's see what that actually does to our graph. So again, I'm going to start with my axis of symmetry. And my axis of symmetry is going to be located at x equals -b over 2 times a. So that gives me -4 over -2, which shows up at +2. All right, so at +2, my axis of symmetry is located. I can find my y-intercept very easily. My y-intercept is going to be at -5. So I'm going to just plot some of those important points. So my axis of symmetry is going to be located at 2. So this is x equals 2. And my y-intercept is at -5. 1, 2, 3, 4, 5. That's where we're going to cross the y-axis. All right, so I'm going to build my table of values. So my table of values, my input is x. I'm going to throw it into the function -x squared plus 4x minus 5 to get my output. And I'm going to start at 2, picking 2 points to the left and 2 points to the right of 2. I'm going to plug in those values. So if you need to pause the video and plug those in, go ahead and do so. So 0 gives me -5, 1 gives me -2, 2 gives me -1, 3, -2, and 4, -5. So you can see very quickly, here's my vertex, and these are my symmetrical values. They should be the same. So we already plotted 0, -5. I'm going to plot 1, -2, 2, -1, 3, -2, and 4, -5. So you can see in this graph, our parabola is upside down. Now our parabola is upside down because of that -1 in front of our quadratic term. That -1, just like it did in an absolute value, it took our v and flipped it. It's taking our parabola and it's flipping that. So that negative is a very important value. That's what happened in those arcs under the bridge. They had to make a negative quadratic function to build those arcs. All right, so let's talk about our important pieces. Our domain from left to right is going to be all real values. Our range this time is going to start at our vertex, but it's going to get smaller. So our range is going to be all y values such that y is less than or equal to -1. That means that this vertex here is not a minimum this time. Our vertex is actually going to be the maximum point. and that's going to give us a value of 2, -1, where -1 is the highest y value in my graph. That's my maximum point at -1. All right, so let's look at why that graph actually flipped. So if we're looking at our standard function, ax squared plus bx plus c, what happens is when a is greater than 0, or when a is a positive number, my graph is going to be positive. It's going to open up, and that's going to create my vertex to be a minimum graph. However, when a is less than 0, or when a is negative, that means that my graph is going to have a maximum function, and it's going to open down because it's going to flip my parabola. So you would get your range of values depending on whether you had a minimum or a maximum value in your parabola. Now, in our next lesson, we're going to continue graphing quadratic functions, and we're going to investigate some real life problems to use these graphs accordingly. If you have any questions, please send me an email. I hope you have a great day.